Hello everyone, this is Mr. Kaviani, and in this video we're going to explore circular motion, centripetal acceleration, and centripetal force. By the end of this video, you should be able to characterize the motion of objects undergoing circular motion, quantify their tangential velocity and centripetal acceleration, and apply Newton's second law to calculate the centripetal force on an object. We're going to take a look at some various examples and look at the different common forces that cause circular motion. Part of this video is going to be to describe circular motion, but the other part is going to ask the question, why do objects travel in circular paths at all? So by taking a look at some examples, hopefully it'll illustrate the idea that many different forces can be responsible for causing an object to travel in a circular path. Let's take, for example, a car traveling along a curved road shown in the first image on the left. What force do you think is responsible for causing that car to continue traveling in a circle? This may not be very intuitive, but the force of static friction is actually responsible for keeping the car traveling in a circle. This is a force that acts between the wheels of the car and the road. And I know you'll say, but the car's moving. How can it be static friction? Static friction acts uniquely for rolling objects like a wheel rolling across the surface. And so we'll take a look at how static friction behaves in detail in a later video. But for right now, we should recognize that static friction is a force that can cause circular motion. You can imagine that if the road were iced over on a snowy day, that it would be very difficult to make this turn. And so that's also proof that friction has something to do with the fact that this car is able to turn in a circle. For our second example, let's take a look at a roller coaster loop. Now, as the roller coaster car is traveling upwards, the roller coaster car is being pushed against the track, and it's being redirected essentially into this circular path. And so what we can say is that in the case of a roller coaster, the normal force provided by the track on the car and the people is responsible for keeping them moving in a circular path. For our third example, we'll take a look at an example of circular motion outside of our Earth. We have a satellite orbiting the Earth. And so if we think about the circular motion of this satellite as it makes a circular path or circular orbit around our planet, there's some invisible force, one that we can't see and one that doesn't require contact between the Earth and that satellite. And what we'll take a look at in another video in more depth is the universal law of gravitation, which describes the gravitational force of attraction between any two objects. Remember, it's not just two objects on Earth. So we also know that the force of gravity can cause objects to orbit or to travel in circular paths. And if we look at our last example, this is actually an example of an athlete with a hammer throw. This is a sport involving a ball attached to a chain that is spun around. And so what we can see is that the ball attached to the end of this chain would not move in a circle if not for the force of tension in that chain. And so tension is also a force that can keep objects moving in a circular path. I'd like to take a moment here to point out a distinction between circular motion and rotational motion. Circular motion is the motion of an object in a circular path where the point about which it's rotating or moving about, a circle, is outside of that object. So what I mean by that is if you look at the car traveling on this curved road, the center of that circle is right here, right? So the car is traveling along a curved path that is outside of itself, right? The car itself is not rotating, and the car is traveling in a circular path. And so we can also, we'll see in a moment, think about the force causing circular motion to point into that circle. So this would be the force of friction pointing into the circle, and we'll take a deeper look at that in just a moment. This roller coaster, again, the cars are moving around a circle where the point of rotation or the point of the circle, the origin of the circle, is right here. That is the point about which those cars are moving. And so the normal force will point into the center of that circle, right? Keeping them moving in that circular path. When we think about a satellite orbiting the Earth, right? The satellite itself is not attached to the Earth. So the Earth is a center of motion for that object, right? It is moving in a circular path around a fixed axis, if you will, which is the center of the Earth. And so we know that the force of gravity, right? The force of gravity must be pulling that satellite into that circle. And in the case of the hammer throw, the hammer itself is not directly attached to the person. So if I think about the person's hands, right, as that center of circular motion for that object, it is rotating about a circle that is formed by the person's hands. Then this would be the force of tension, right, pointing into the center of that circle that it's creating. So it would move in a path like this if it were to continue to move in that circular path. So I just want to point that out. Circular motion is the motion of an object in a circular path where the axis of rotation, if you will, or the point about which it's moving in a circle, is outside of the actual body of that object. All right, now that we've seen some examples of circular motion, let's take a look at how we can quantify and characterize the motion of these objects.